This is section 7.3, volume, the shell method. So this time we're going to be finding a volume of a solid of revolution in a different way. Before, in the last section, the first part of it, we found volumes of solids of revolution using a disk or a washer. And this is an alternative to that and will really make your life a whole lot easier if you know how to do it as well as the other one, the disk washer method, because it makes that, like that problem where we had to set up two integrals, that one's easy and it's one integral and boom, you're done. So let's talk about what this will look like. So let's say we have a function, some function f of x, and to make it easy, I think I'm going to start with it going from x equals 0 to x equals some number. Well, okay, yeah, I'll do that. That's fine. So from A to B. Okay. So, and this time, when I'm asking you to work with this, you realize that your function is an f of x. You'd really like to use a delta x in your work, so a delta x rectangle, and so we draw one of those, hoping that that's going to be correct. And so that's delta x wide. But what we're revolving around is not the x-axis. Let's go around the y-axis. See, when we did the disk and washer, something I didn't tell you, because it's the contrast that's important. You didn't have to know this at the time. But anytime we were doing a disk or washer, let's make this washer to make it easy. Every single time we did that, the rectangle that we drew, like a delta x rectangle, had what orientation to the axis of revolution? Let's just say it was the x-axis that we're revolving about. What's the relationship? Well, it's perpendicular, right? The rectangle is a vertical rectangle, and its length is perpendicular to the axis of revolution. So our rectangle is perpendicular to the axis of revolution. And in fact, if that's the orientation that you have, you are definitely using the disk/washer method. And you know the difference is, of course, that you have a disk unless there's space, which creates a hole in the middle of the solid. And so it's really the same method, just a little bit more complicated when it's a washer. So that perpendicular nature means that you're doing the disk or washer, because remember, as you revolve that around, it creates that disk in this case. Okay, so this time over here now, when we revolve this around, think about that rectangular strip going around the y-axis and leaving a solid in its wake. And you won't see it when it's out of this plane, but at 180 degrees through your revolution, that one rectangular strip will pass back through the x and y plane and then continue around the rest of the way. And to draw these, it's really pretty cool. If you just draw little elliptical things from the top edges of the top edges of the rectangles that you've drawn, you'll get a sense of what it is we're getting. That's called a cylindrical shell. And for you to visualize what that is, I'd like for you to consider if you've ever used one of those devices that you use to remove lint and pet hair and stuff from your clothing. And that's concentric pieces of sticky tape that when you roll and get all the stuff, and finally that thing gets so clogged it doesn't pick up anything. And you tear that strip off because it's perforated, and think about what you had. That was something that went all the way around the device, and when you peel that off, you've got a layer underneath that's a slightly bit smaller because it's closer into the middle. And that piece that you tore off, if you were to lay it down on the table, it might look something like this. Here's that strip of tape that you pulled off. I'm not going to draw the little cat hairs and stuff on it. Just imagine those. And it actually has thickness. It's a very thin piece of tape, but it has thickness. So in essence, that shell that was around that cylinder, when cut and unrolled like this, is a rectangular prism. Okay, so this up here is that piece of tape. This graph is like a picture of that piece of tape as it's existing on the roll. And you cut it, roll it out, and you get this rectangular prism. And so we need to make sure we understand what the dimensions are of that. The height of that cylinder, is, in this particular case, the distance from the x-axis to the curve is a measure of y, which we'll use f of x because it's delta x. We want to use x's instead of y's. And that is this dimension down here. Okay? Because this unrolled to this, and I'm thinking of this as being the height of the cylinder originally, is that dimension. The thickness of this little prism is our delta x. And the only remaining question is, in my mind, is what is this length? And if you imagine where that came from, that was the piece of tape wrapped around the cylindrical lint roller. And when that was torn off, what was that length before it was torn off? Well, it was the length around the cylindrical tube that you've got there. And so that length of this is actually what we call the circumference of the circle up here. So there's a circle right there, and its circumference is what we're finding down here to be the length of this rectangular prism. And you should know that the circumference of a circle is 2 pi r. And so we're going to have to know what r is. And if we look at this picture, and this will be an always true thing, the radius, it goes from the axis of revolution to the location of your rectangle. Okay, so we're going, in this case, from the y-axis to that is a measure of x. And so the radius is x. And so this would become 2 pi times x. So if we wanted the volume of one of these cylindrical shells, this is the ith volume, the volume of the ith rectangle revolved around there. It's going to be, for a rectangular prism, length times width times height. So the length is 2 pi times the particular x that's being used right then for that one shell. So It's the x value where the rectangle is touching the curve, x sub I. That's the length times the width, which is f of x, whatever that happens to be. I'll call it f of x sub I. And what we'll do there is substitute whatever the actual function expression is. Times length times width times height is delta x. So then we're going to add up n such rectangular strips that are rotated around to get an approximation of the volume of that solid. Then we're going to press the widths of all of those to go to 0, and if we use equal widths, we can say that that's the limit as n approaches infinity of that expression in sigma, and that becomes our definite integral from a to b of 2 pi x f of x, and delta x becomes dx. So in general, a little bit more general than that, this will be the radius of the cylindrical shell, the cylinder that it comes from, and that'll be some function of x. And the f of x will be the height of the cylinder as drawn in the original graph. Okay, so that's the basic idea, and I have some pictures in there that kind of show how all that comes about. They're prettier pictures than I could draw. So let's look at one in particular. Has a kind of an interesting picture that you can see half of the cylindrical shell, the part that's behind the xy plane, and it's just one of those. So let's actually look at this one. The function we're dealing with in this example is y equals 6x minus x squared. Between the x-axis and the curve, okay, so the x-axis and that curve are the boundaries of our region, and we're revolving about the y-axis. Okay. Now, a good part of the discussion now is going to be sort of strategic, if you will. If y is given as a function of x, that means I really want to use delta x. And generally speaking, that's going to be something that we want to stick with. And if the information, on the other hand, is given where x is some function of y, then that would mean that we want to use delta y. So what I would do is draw a picture of the graph of this. This is a parabola that opens downward because the coefficient of x squared is negative. If I set the function equal to 0, that will allow me to find the x-intercepts. Common factor being x, leaves 6 minus x. And the things that make that 0 are 0 and positive 6. And so I'm going to go out here to positive 6. That's one of my x-intercepts. 0 is the other. This is a parabola that's opening downward, so its vertex is halfway between 0 and 6, and opening downward. This does not have to be a perfect picture. Again, I'm trying to stress that this is an idea generator more than anything else. Okay, then we made a decision a few minutes ago that we would use delta x. So I'm going to draw a representative rectangle that's delta x in width. Then I'm going to look at the axis of revolution that I'm given. This is about the y-axis. And I'm going to notice that the y-axis, that vertical line, is parallel to my rectangle. And when that's the case, when we have a parallel situation, when they're parallel, so the rectangle is parallel to the axis of revolution, that means that we are actually using cylindrical shells. A lot of people will abbreviate that and just say shells for short, so using the shell method, but it's actually cylindrical shells, the full name of it. So, because of the parallel y-axis to our vertical rectangle is the case, that means we're using shells. Now, you don't have to do what I'm about to do, but I like to draw an image of that representative rectangle as it goes around the axis of revolution, trying to use some symmetry just so I can kind of see the cylinder that's created. Okay, so when I pretend like I cut that, it's perforated tape or whatever, and roll that out, you get a rectangular prism. So it's got some thickness to it. The thickness, of course, is our delta x that we already identified. The height of this one is the height of the rectangle, length of the rectangle is the height of this cylinder. And because we're going from the x-axis to the curve, that's a value of y. So this is f of x. And the length is the circumference, which is 2 pi r. And then we need to rewrite that r as a function of x. So we need to look at, very carefully look at the cylinder that I drew. The axis of revolution is the center of it, and we're going from there to the rectangle. And going from the y-axis to the curve is a measure of x. So r is x. The radius of that is x. And so we can replace that and say that's 2 pi x. Then what we're going to do is find the volume by using the idea of we're going to integrate length times width times height. That 2 pi constant I'm going to pull out in front, generally speaking. So 2 pi x, the x stays inside. There's my length times my width, which is the function 6x minus x squared. And I could have written that up here as well. Probably would have been perhaps a bit clearer that that's what I'm using. So I've got length 2 pi x times width 6x minus x squared times height, and the height, of course, of the prism is delta x, and that becomes dx in the integral. And since it's a dx integral, we have to look at the original region that was graphed. Make sure you don't look at that image that I drew on the left side of the y-axis, but the original image, what's being revolved around. What are the boundaries, low and high boundaries of that region as far as x values are concerned? Well, it starts at x equals 0, and the region ends at x equals 6. And there's your integral. So let's practice this one, practice a little bit of calculus 1 to actually finish this one. So I need to find the antiderivative. Before I do that, I'm going to see if this will simplify. And I think distributing that x is a good idea. Simplify first is always a good idea with integrals. Then the antiderivative of that is 6x cubed over 3, so 2x cubed is what that simplifies to be, minus 1/4 x to the 4th. evaluated from 0 to 6. So we substitute in 6, the upper bound first. For each x, we substitute in a 6, minus, and then we substitute in the 0 in for each x. And then do the arithmetic, and you should get 216 pi when you complete this. Okay? So that is the cylindrical shell method. So I'm going to skip by a lot of the theoretical explanation because it's a lot like what we've talked about before. It's the same theme. And I kind of discussed it earlier where we form a sigma expression for the length times width times height, and then make the magnitude of the size of the widths go towards 0, which is the same thing as n approaching infinity if the width of every interval is the same. And they came up with a generic looking thing. They use p and h, which I don't use that, so that's why I'm kind of skipping over it. What I would make sure that you realize is that p is the radius. So I'm going to rewrite their formulas in a way that I find more useful. So the volume will be either 2 pi times the integral from a to b of a radius function times a height function dx. That's length times width times height. Or if it's oriented the other direction, this would be from c to d, a radius function in terms of y, times the height of the cylinder in terms of y dy. And let me just say that if you have a cylinder that looks like this, which comes from a delta y situation, the height of it is this dimension. Okay, it'll be on its side, so you need to realize that that'll be your height. And of course the radius is from the axis of revolution to the rectangle, and so that radius will be a function of y right there for that length. Okay, so let's, I think, go right to some more examples so that we can make sure that this is clear. Let's say that the region is bounded by y equals x minus x cubed, the x-axis, and we're staying between, including 0 and 1. Okay, so I'm going to use the part of the graph of x minus x cubed that will be used in this problem, and it looks something like this, between 0 and 1. Not exactly, but something like that. Because of the information that's given, I want to use delta x because y is given as a function of x. So that means I'm going to have a representative rectangle that's delta x wide. Then I'm going to pay attention now to the axis of revolution, and that will determine which of the two methods I'll use, disk washer or shells. So I read the question a little bit further, and it's supposed to be about the y-axis. All right, so I think about the y-axis and the fact that it is parallel to my rectangle, and that means, of course, I'm using cylindrical shells. So again, you don't have to draw this part I'm doing here right now. This just helps me get my thoughts in order. Okay, so I see a cylinder. When I take that cylinder and cut it and roll it out, I get that rectangular prism, the width of which is the length of my rectangle, and because that's the distance from the x-axis to the curve, that's y. Since we're using delta x, I want to rewrite that in terms of x, and so this y will be x minus x cubed. The thickness will be delta x, and the length of my rectangular prism is the circumference, 2 pi r. So I need to determine how big r is. It's the distance from the center, the axis of revolution, to the rectangle. That's a measure of x, so r is x, and so this is 2 pi x. All right, so the integral, therefore, it would be 2 pi times the integral from, now the original region goes from 0 to 1, so make sure that that's what your bounds are, 0 to 1. So 2 pi x is the length, the 2 pi has just been pulled out, times the width, which is x minus x cubed, times the height of the prism, delta x, which becomes dx over here. And that's the setup, and I'm going to leave this one to you to do for practice on your own, and you can look at the answer here and make sure that you agree with this answer. This is a good one for you to practice your Calculus 1 skills. You should get 4 pi over 15. And again, you should be able to do this without a calculator sometimes. This one wasn't too bad. Okay, so let's do another example. Find the volume of the solid obtained when the region between y equals x squared minus 4x and y equals 4x minus x squared is revolved about the line x equals 10. So the reason I wanted to do this one is because very often the axis, revolution about an axis is what the examples show, and then they don't show you that many examples where the axis of revolution is another line that's not one of those. Of course, we can only use we can only use the vertical and horizontal lines for this. They could be the axes, one of the axes, or it could be like this one, a vertical line at x equals 10. Okay, so let's graph this. Let's see, the x-intercepts of both graphs are at 4 and 0. So, and I'm going to call this one y sub 1, is one that opens upward with these two x-intercepts. So let's just say that the vertex, it has to be halfway between 0 and 4, is about that low down. Notice I don't even put a scale on the y-axis here because it's, like I said before, this graph is a thinking piece. It doesn't have to be perfect, it just needs to be good enough. And then I'm going to call this one y sub 2. That's a parabola that opens downward, and its x-intercepts are also 0 and 4. And so let's say it looks like this. So this was y sub 2, and this one was y sub 1. And because my information is given where y is a function of x, I'm going to draw a rectangle that spans the region that's delta x wide. So it needs to go from one curve all the way to the other. And that's what's going to be revolved about the line x equals 10. Now obviously this probably won't be to scale, otherwise I won't be able to fit it well. So let's just pretend like 10 is here. It's not really, but let's pretend like x equals 10 is that close. And we're revolving about that. And so my image of that rectangle in red as it goes around here, I'll try to draw it so that it's at least looks sort of close. When it gets back to the plane, it'll be about right there. And this will look really nasty, sorry, because I can't draw these ellipses that well. Okay, well, pretend. And of course there's stuff down here too. All right, anyway, pretend like that's a really good picture. It's not, but I'll accept your false statements of just how good it is. Of course, when we cut that cylindrical shell, and I knew I was using shells, but by the way, I didn't mention it, but I just thought it in my head and just went on. Because my rectangle and my axis of revolution are parallel to each other, that is what tells me I'm using cylindrical shells. So the thickness of that is delta x. The width of the rectangle is this dimension right here. And this does not measure from the x-axis to something. So remember what we do here is when we have two functions, to get the distance between them, we take the top one minus the bottom one. Oops, I probably should have written that in terms of what we called them. Hold on, sorry. So which one's on top? That's y2. That's what I meant to write. Minus, which one's on bottom? Right, y1. And so over here, what I'm going to write for this length is, by substitution, y2, which is 4x minus x squared, minus y1, which is x squared minus 4x. And if I were you, I'd go ahead and simplify that. So 4x minus negative 4x is 8x. Negative x squared minus x squared is minus 2x squared. That'll be a much nicer thing to take into our integral in just a minute. Okay, this dimension, the circumference of that circle, is 2 pi r, and this is probably the hardest part of this, besides the width being y2 minus y1, which we've encountered before. This one is a little bit dicier, and that's why I really want to have a pretty decent picture so that I know what's going on. The radius of this goes from the axis of revolution to the original curve. Make sure you don't go over to the right in this picture. You have to go back to the original curve that's there. Okay? That's the radius in orange. Now, to figure this out, let me draw a couple of things to your attention. If I went from the y-axis to the axis of revolution, that's always 10. If I were to go from the y-axis to the curve, that's measured by x. So if you look at the things I've drawn, the length 10, the length x, and the length r, how are those three things related to each other? Well, I'm hoping that you see that r is the total length 10 minus the length x. Okay? So this is not a simple x, this is a 10 minus x. So it'll be 2 pi times the quantity 10 minus x for the circumference, the length of that rectangle. Okay, so now the volume is the length, which is 2 pi times 10 minus x. I'm pulling the 2 pi out. So 2 pi times integral 10 minus x. So that's length times width, which we simplify to be 8x minus 2x squared, times thickness becomes dx. And looking at the original region that we revolved around the line x equals 10, what are the lower and upper bounds of the x values used for the original region? And that's 0 to 4. Okay, so this is another good one for you to try to do all by yourself. Hopefully the first thing you'll do is simplify that integrand first. Oh, I wasn't going to do this for you. Oops, let me take that back. But you'd simplify that integrand by multiplying the two polynomials together and then integrate the polynomial answer and do the antiderivative and substitute 4 into that minus substitute 0 into that. And again, that's good practice for you. This ends up being 1024 pi over 3. Make sure that you can get all the way there, showing all the steps as we've seen before. Now, if this problem had been set up an integral that would find that volume and then use your calculator to find an approximation of what that volume is. And so if you typed using Math 9 this expression up above, you can double check yourself that the decimal answer you get is 1072.330. And that too would be a really good thing to practice. This is a kind of complicated looking one. This would be a good one for you to practice on. Okay, the next slide says comparison of disk and shell methods. And actually, I've done most of that already. We've already kind of talked about it. So for the disk method, the representative rectangle is always perpendicular to the axis of revolution. Said that way earlier. For the shell method, however, the representative rectangle is always parallel to the axis of revolution. And they've shown you several pictures of that. So if you'll recall, there was a problem we did last section that I said we'd come back to and do a smarter way. So if you want to look back at your notes from that or re-look at that recording to get that fresh in your mind, that's great. I'm going to start as if you remembered it perfectly. So we had a function that went like this, and we were going from 0 to 1. And so our region looked like this, and we were revolving this about the y-axis. And what we did at that point in time was we said, oh, well, and I didn't articulate this at the time, but we were using delta y because we were told to. And if you use delta y, there were two versions of delta y that were possible. On the lower part, it would go from the y-axis to the vertical line, but once you got to this point right here, you'd have to change gears, and your representative rectangle would go from the curve to the vertical line. And so you'd have two different integrals that we set up. We went through all that, and it was kind of painful, and I didn't like it, and I'm hoping you were kind of like disgusted with it too. So let's talk about how to do it the right way. So I'm going to redraw this so I don't write over the stuff that I've already drawn. And of course this curve was part of y equals x squared plus 1. Just to remind you, that was the curve. And this went from 0 to 1. And y equals 0 was another boundary. So it's this region right here that we're revolving. Now, what I'd like to do, which I couldn't do last time, if you remember, in using delta y, we were forced to find an expression in terms of y which meant we had to solve, not solve that, excuse me, I'm pointing the wrong thing. We had to solve this equation for x. And if you recall, it was the square root of y minus 1, which meant we had a radical to deal with, which wasn't pretty and that wasn't fun. And what I'm trying to say is you don't want to do that. You don't want to have to solve for the other variable. The only exception to that would be if it's like the equation of a line or something else that's pretty simple. If you were given this line as one of the boundaries and you decided you really wanted to use delta y for that problem, this one's easy enough to solve by subtracting 3 from both sides and then dividing both sides by 2. That's easy enough to solve for x that if you need to, do that. If it's delta y that you really want to use in the problem, you'll want x as a function of y, and that won't be hard to find if it's a line, something simple. But if it's anything complicated, you're not necessarily going to even be able to solve for that variable. Like if I had y equals x plus cosine x, can you solve that for x as a function of y? No. You don't know how to do that. So you couldn't even do that with that problem if it came up. Y equals x squared plus 1, oh yeah, we could solve for it, but it did make us have to deal with a radical. And we had to do 2 integrals. So let's now do it the smart way. Since y is a function of x, that tells me that I should use delta x. So I'm going to draw a delta x rectangle. And notice this time, that representative rectangle represents everywhere, because at the top it'll be touching the curve, at the bottom it'll be touching the x-axis no matter where I draw it, which is a good thing. Okay? So our axis of revolution again was the y-axis, and so the image, when we go 180 degrees through our revolution, will be somewhere over there like that. And then we cut that and roll it out to get our rectangular prism. Ooh, wow, that was not drawn very well. Yikes. Of course, this is delta x wide, so that's delta x thick. This dimension is the y value because we're going from the x-axis to the curve, which since it's delta x, instead of writing y, I'll want to write what y is equal to in terms of x. And again, that's why we wouldn't want to do this one, because we might not be able to express x as a function of y always. So you want to kind of leave it in the form it is. And then this dimension, the length of the rectangle, is 2 pi times r. Now we have to figure out what r is. R is the distance from the axis of revolution to the curve where the rectangle touches it. Since we're going from the y-axis to the curve, that's a measure of x. So r is x in this problem. R is x. So the definite integral we'll set up is, the volume is length 2 pi x, 2 pi I'm going to bring out of the integral x, 2 pi x, times the width of the rectangle, which is x squared plus 1, times the thickness of the prism, delta x, which becomes dx. And we'll integrate this from the low x of the original region, 0, to the high x of the original region, 1. And if you finish this problem out, you'll see that you get 3 pi over 2, like we got last time, but with a much more complicated setup. So I think you'll agree that this is a way easier approach to this problem. And that's what I would recommend, is allowing yourself to figure out, based on first how the information is presented. If x is a function of y, if that's how it's given, then use delta y. Oops, it's supposed to be y. Let me try that again. That didn't look very good. I actually wrote an x. So delta y. However, if y is given as a function of x, which is a lot of them will be like that, then that means you want to use delta x. Then once you've drawn a good graph of your function in your region and draw in your representative rectangle, if you have parallel, the rectangle is parallel to the axis of revolution, that means that you're going to use shells. And what that would look like in the first case would be if delta y is your rectangle, then the axis of revolution would be something parallel to it, so something above it or below it, like that. And if it's a delta x situation, which will look like this, shells would be because this is parallel to your axis of revolution, something vertical. Could be to the right of it like I've drawn, or to the left. Now, reviewing what we already talked about, however, if they're perpendicular to each other, that means we're using disk or washer method in both situations. And so what that would look like is if you had a delta y situation and the axis of revolution were a vertical line, either to the left or to the right of it. I should probably draw little arrows saying that's the axis of revolution, so that's very clear. Okay, and then if it's a delta x situation, perpendicular to that would be perhaps something below it, or it could be above it. It's an axis of revolution that's perpendicular. And so that's how I would run my thinking process. Figure out if you're using delta x or delta y, draw your curve, draw your representative rectangle that has either delta y or delta x orientation, figure out if that's parallel or perpendicular to the axis of revolution, and that will determine which of the two methods will be best. As you saw, that one problem that we did last time and then did it again this time using the cylindrical shell method, sometimes you can do it the other way, it's just a lot messier. Sometimes you can't do it at all. So you might want to really pay attention to this discussion, because I've tried to give you a really good indication about how to know which of these two methods is going to be the most appropriate in any given situation. Okay, that ends this lesson. I will see you in class.